Hello, gentlemen. I'm glad you're viewing this video. This video is an introduction to variable manipulation. And that's a fancy word, fancy term that just means we're going to start looking at equations instead of in terms of numbers, in terms of the variables themselves. I'll give you an example of what I mean. We've been using equations to describe phenomena in physics all year. And one of the equations that we've been using a lot recently is the friction force equation. So I'll put that up here. Friction force is equal to the coefficient of friction. In this case, we're going to talk about kinetic friction times the normal force. You guys are used to seeing that equation. You're used to using it too. If we know the coefficient of kinetic friction and the normal force, we can calculate the friction force. In fact, if we know any two of the variables, if we know any two of friction force, normal force, or the coefficient of friction, we can plug those two values in to calculate what the third one is. So, for example, let's say that we know by our physics equipment that the friction force acting on some object were equal to 80 newtons, while the normal force acting on that same object were equal to 100 newtons. Well, I think you could tell me pretty easily what the coefficient of kinetic friction is. But here's what I want you to do. Instead of plugging in those numbers right away, I want you to rearrange the equation so that only coefficient of kinetic friction is on one side of the equation. I want you to get rid of all the other stuff, move it to the other side of the equation, and then plug in the numbers. Here's what I mean. I want to get the coefficient of kinetic friction all on its own on this equation. So I'm going to divide the normal force over to the other side of the equation and end up with an equation that says friction force divided by normal force is equal to the coefficient of kinetic friction. Great. Now I have what I'm looking for all on one side of the equation and all the rest of all the other variables on the other side of the equation. Now I can plug in those two values of those variables. Friction force is equal to 80 newtons and normal force is equal to 100 newtons. And I find out after I run this calculation, very straightforward calculation, that the coefficient of kinetic friction is equal to 0.8. Well, great, Mr. Schumacher. I think that's something we could have done before, and I agree. This is a very easy example meant to illustrate the technique that will become useful as the problems become more difficult. So let's try another example. In this example, let's say I am in a very familiar situation for our physics class and physics homework problems. A man pulling a box with a rope. Let's say this man is pulling a 15-kilogram box. So the mass of the box is 15 kilograms. He's pulling with a tension force of 200 newtons. And finally, we know that the coefficient of kinetic friction is equal to 0.5. Now, this is a pretty standard set of circumstances. We know what the coefficient of kinetic friction is. We also know how hard the man is pulling and how heavy, not how heavy, how massive the box is. But if we want to solve for example, what the acceleration of the box is, and for those of you trying to use this to solve a problem, this is very similar to one of the problems in your current homework set. This is a relatively straightforward problem. So it wouldn't surprise me if you've solved this problem without the technique that I'm about to show you. But I think it will be useful for seeing how the technique works. If I want to solve for the acceleration of the box, first, what I'm going to do, no matter how I'm solving this problem, is draw a force diagram. I know that I have gravity force acting on the box downward. I also have normal force acting on the box upward. The man is pulling the box, we'll say to the right, in this example. And friction force is opposing the motion of the box. The box is moving, it is accelerating, and that's why we have the coefficient of kinetic friction. So there's my force diagram. I'll complete it by drawing a set of coordinate axes. And the way I'm going to solve this is just like any normal way of solving this problem. I write my two equations. The sum of the forces in the x direction is equal to the net force in the x direction. Similarly, the sum of the forces in the y direction is equal to the net force in the y direction. Now, I'm going to plug in the forces that are actually acting in the x direction. Those are the tension force, which I'll abbreviate with a T from now on, and the friction force, which is acting in the negative x direction. So we'll remember to put our negative sign on there. Finally, the net force is equal to, by Newton's second law, the mass of the box times the acceleration of the box in the x direction. I'll do the same thing for the y equation. I know that there's normal force acting in the positive y direction and gravity force acting in the negative x direction. And all of that is equal to the mass of the box times its acceleration in the y direction. This setup we've used plenty of times before, and I expect that you should be able to get to this point on your own. Now here's the power of our setup. I am looking for the acceleration of the box in the x direction. We actually already know that the acceleration of the box in the y direction is 0 meters per second squared. So I'm looking for the acceleration in the x direction. And if I'm going to solve for that, before I plug any numbers in, I want to get that all on its own. So watch how I do this. I'm going to use the x equation and move every other thing to the other side. Now in this case, the only thing along with the x acceleration is the mass of the box. So I'll divide that to the other side, and I'll end up with this equation. Now it's clear that if I knew the mass of the box and the tension force and the friction force, I could plug all those values in and calculate the value of the acceleration of the box. Now I do know the mass and I do know the tension force, but I don't know the friction force. So I'll substitute an equation that we have for the friction force, the one that I showed in the last slide. The friction force is equal to the coefficient of kinetic friction times the normal force. Great. Now if I knew the mass and the tension force and the coefficient of kinetic friction and the normal force, I would be able to plug all those values in and solve for the acceleration of the box. But I don't know the normal force yet. I can get it, though, from the y equation. Let's go find out how big the normal force is. Normal force is equal to force gravity because the acceleration in the y direction is 0. Now we're getting somewhere. I have 1 over mass times the tension force plus negative coefficient of friction times gravity force all together equals the acceleration of the box in the x direction. Now, if I knew the mass and the tension force and the coefficient of friction and the gravity force, I could plug them all in and solve for the acceleration in the x direction. But I don't yet know the gravity force. But I have an equation for it, so I'll plug that equation in. You'll notice I'm not putting any numbers into this equation. I'm using only variables. Now, at this point, I am going to use one number because the equation for gravity force tells us that gravity force is equal to 9.81 newtons per kilogram times the mass. And now, I do know all of the things on the other side of the equation. I know the mass and the tension force and the coefficient of friction. Mass is repeated at the end. I can plug in all those numbers, plug them all into my calculator at once, and solve in one step for the acceleration in the x direction. So let's try it. The mass is 15 kilograms. The tension force is 200 newtons. The coefficient of friction is 0.5. Mass, once again, is 15 kilograms. And when I plug all of that into my calculator at once, I end up with the acceleration in the x direction is equal to 8.43 meters per second squared. One step, I solved the entire equation. And if that were all I needed, I'd be done at this point. There's an illustration of this method. And you might even at this point be saying, but Mr. Schumacher, I could have done that without this method, and I plug in my numbers at the beginning, and I find out what the normal force is, and I plug that number into my equation, and I can solve for the x acceleration earlier. I'll assure you that you're actually doing all of these steps, you're just doing them with numbers. But the benefit of using this method is in cases where plugging in the numbers too early makes the equation either very difficult or maybe even impossible to solve. So I'll give you an example, one that's similar to another one of your problems, where you're not told the mass of the box. And you'll complain to me that it's impossible to solve because the mass is unknown, and without the mass being known, we can't solve for the gravity force, and that throws a lot of things off. So I'll show you an example of how to solve a problem where you don't know the mass of the object. It's not going to be exactly like the problem that you might be dealing with, but it will once again demonstrate the method. The Apollo missions used the Saturn V rocket to get them to the moon. So the Saturn V rocket, you can look up on Wikipedia, has a thrust of 34 million newtons. And at liftoff, when it was fully loaded, the acceleration of the rocket, the whole vehicle, in the y direction, obviously it was going straight up, was equal to about 2.3 meters per second squared. This is not a very large acceleration. The acceleration became larger as the rocket burned fuel and became lighter. But at liftoff, its acceleration was about 2.3 meters per second squared. Now, with this information, we can solve for the mass of the rocket. And I'll show you how. Just like normal, we're going to start by drawing a force diagram. Let's remind ourselves what we're looking for. Mass is unknown. There's thrust pushing the rocket up. There's also gravity force pulling the rocket down. And there are no other forces acting on this rocket, not major ones, not at liftoff. Air resistance becomes more important, but at liftoff, the rocket is moving slowly, so air resistance is not a problem. And since all the forces are in the vertical direction, all I'm worried about is the y direction. So all I need is one equation. The sum of the forces in the y direction is equal to the net force in the y direction. I plug in the forces in the y direction, F thrust, and gravity force, which is acting in the negative y direction, add up to the net force in the y direction, which is equal to the mass of the rocket times its acceleration in the y direction. Okay, now we haven't done anything differently yet. But in order to solve this problem, I'm looking for the mass of the rocket. So what I'm going to do is plug in, because I know that the gravity force depends on mass, I'm going to plug in the equation for gravity force right now. Gravity force is equal to 9.81 newtons per kilogram times the mass. And so I'm left with this equation. Now, if I'm solving for the mass, I need to get all the mass on one side of the equation. So in order to do that, I'm going to add the term in this equation that used to be the gravity force to the other side of the equation. Once again, these are just ordinary rules of algebra. I'm not inventing any new math rules. All the math is the same. I'm just doing this problem in terms of variables instead of numbers. Now, I need to get all the mass on its own. So I'm going to use the distributive property to collect mass, both mass terms, outside the parentheses. And I end up with mass times 9.81 newtons per kilogram plus the acceleration all together. Now you can see how to get mass all on its own. I have thrust. I divide 9.81 newtons per kilogram plus the acceleration in the y direction to the other side. And I am left with, on the left side of my equation, only mass. Now this is the situation I want to be in, because I know the thrust and I know the acceleration. Since I know those two things, I can plug them into this equation and solve for how big the mass is. So let's do it. The thrust is 34 million newtons. And the acceleration is 2.3 meters per second squared. Now, we have to be careful. Some of you might be noticing, Mr. Schumacher, you're not allowed to add things that don't have the same units. And newtons per kilogram and meters per second squared don't look like the same unit. But if you remember, a newton per kilogram is equal to a meter per second squared. So if you notice that, very good, good for you. But rest assured, these units actually are equal, so we're allowed to add them. I plug that into my calculator, and I find that mass is equal to approximately 2,810,000 kilograms. That is the method. This method will work for solving equations that seem to be unsolvable when you plug in for numbers immediately. So give that a try. If you would like some more practice problems, I can give those to you. Please email me or send me any questions that you have. Also ask in class or after class, and I'll be happy to help you. Good luck.